The concept of the multiverse has long fascinated both scientists and philosophers, bridging the boundaries between empirical science, speculative theory, and metaphysical inquiry. At its core, the idea poses a simple yet profound question. Is our universe unique, or could there be countless other universes existing parallel to our own, possibly governed by different laws of physics or following entirely distinct timelines? In recent decades, this once largely philosophical or science fiction concept has begun to gain serious traction within the scientific community, fueled by developments in cosmology, quantum mechanics, and theoretical physics. And before we continue, please subscribe and leave like for more sleepy science videos. The term multiverse refers to the hypothetical existence of multiple universes, each potentially separate in space, time, or dimensions, and possibly containing different versions of reality. While there is currently no direct empirical evidence for the existence of a multiverse, several widely accepted scientific theories predict or allow for it as a natural outcome of their underlying frameworks. These include cosmic inflation theory, certain interpretations of quantum mechanics, especially the many-worlds interpretation, and various models derived from string theory and M-theory. Each of these fields, originally unrelated in their development, converges on a possibility that our universe may be one of many, suggesting that what we perceive as everything might only be a minuscule fragment of a far larger and more complex reality. The modern scientific method is built upon observation, testing, and falsifiability. This foundation makes the idea of a multiverse particularly controversial. If other universes cannot be observed, measured, or interacted with in principle, should their existence be considered a valid scientific hypothesis? Critics argue that this makes the concept metaphysical rather than scientific, while proponents counter that it is an unavoidable implication of otherwise well-supported theories. As a result, the multiverse debate touches not only on questions of cosmology and physics, but also on the philosophy of science itself. The line between science and speculation is tested when predictions cannot be directly confirmed but are logically consistent with existing theories. One of the main driving forces behind the multiverse hypothesis is the effort to explain the fine-tuning of the physical constants in our universe. Many of the parameters that govern the behavior of particles, forces, and the structure of space-time are incredibly precise. Even slight variations in these constants would have led to a universe where stars, galaxies, or life could not exist. This so-called fine-tuning problem has led some to propose the anthropic principle, which suggests that we observe these constants precisely because we are in a universe that allows observers to exist. In the context of the multiverse, this principle implies that an ensemble of universes exists, each with different parameters, and we simply find ourselves in one that happens to support life. Historically, the notion of multiple worlds is not new. Philosophical ideas about the existence of other realms or dimensions can be traced back to ancient cultures, including early Hindu cosmologies and the Automist philosophers of ancient Greece. However, the transition from philosophical speculation to scientific hypothesis occurred gradually as physics matured in the 20th and 21st centuries. Early cosmologists focused on understanding the origin and structure of our own universe. With the rise of quantum mechanics in the early 20th century and the subsequent development of relativistic cosmology, the scope of these investigations expanded. Eventually, the convergence of different theoretical models opened the door to a serious consideration of other universes as more than just abstract musings. Today, the multiverse occupies a curious position within the hierarchy of scientific ideas. It is simultaneously at the frontier of theoretical physics and a topic of skepticism. Researchers continue to explore its implications through mathematics, simulations, and indirect observational techniques. Some physicists view the multiverse as a paradigm shift, comparable to the acceptance of the heliocentric model or the discovery of relativity, while others warn against investing too much in a concept that may never be empirically verified. Despite this division, public interest in the multiverse is growing, fueled in part by its popularity in science fiction and media. Popular culture has embraced the idea, often portraying parallel realities where characters live different lives based on alternative choices or circumstances. While these fictional interpretations often take creative liberties, they reflect a deep human curiosity about what could have been and about the true scale of existence. This cultural aspect adds another layer to the study of the multiverse. It is not only a scientific and philosophical question, but also one that resonates emotionally and psychologically with people. In academic contexts, researchers approach the subject with varying degrees of caution and enthusiasm. Some use the concept as a heuristic framework for exploring deep theoretical questions, while others attempt to formalize it with rigorous mathematical models. In doing so, they raise challenging questions about the very nature of reality, such as, what does it mean for something to be real if we can never experience it? Is a mathematically coherent universe with different properties any less real than ours? Can science accommodate entities that lie permanently beyond the reach of experiment? The introduction to this project, then, aims to set the foundation for a comprehensive exploration of the multiverse concept. Throughout the following sections, we will delve into the motivations behind multiverse theories, the various forms they may take, and the implications they hold for science, philosophy, and human understanding. We will examine both the supportive arguments that arise from modern physics and the criticisms that question the scientific legitimacy of the idea. Additionally, the project will explore the potential evidence that could, one day, lend credibility to the multiverse hypothesis, or alternatively, prove it to be an intellectual dead end. In a world where the limits of observation define the boundaries of science, the multiverse represents an extraordinary extension of human curiosity. It challenges our assumptions about existence and stretches the scope of what science dares to consider. Whether or not the multiverse exists, the exploration of this idea compels us to refine our methods, sharpen our definitions, and expand our view of the cosmos. Ultimately, the question, does the multiverse exist, may not yet have a clear answer, but the pursuit of that answer drives innovation in theory, methodology, and imagination alike. The purpose of this study is to explore the theoretical and conceptual foundations of the multiverse hypothesis, analyzing the various scientific, philosophical, and cosmological models that propose the existence of multiple universes. This investigation seeks to clarify what is meant by the term multiverse in different scientific contexts, to examine the rationale behind its emergence as a legitimate theoretical possibility, and to consider whether the hypothesis can be meaningfully integrated into the broader framework of modern science. While the study cannot offer direct empirical confirmation of other universes, it aims to assess the internal consistency of multiverse theories and evaluate the ways in which they arise naturally from existing models in physics. A central aim of this work is to illuminate the growing interest in the multiverse among physicists and cosmologists, particularly in connection with problems that remain unresolved within our current understanding of the universe. For instance, the fine-tuning of fundamental physical constants, such as the strength of gravity, the cosmological constant, and the mass of elementary particles, has long puzzled researchers. These constants appear to fall within extremely narrow ranges that make the emergence of complex structures and life possible. One proposed explanation is that there exist a vast number of universes, each with different values for these constants, and we simply happen to exist in one that is compatible with our presence. In this context, The purpose of the study extends to examining how the multiverse might offer a solution to such fine-tuning problems. Furthermore, the project endeavors to clarify the implications of several prominent theories in modern physics that seem to imply the existence of a multiverse, even if unintentionally. Cosmic inflation, for example, originally proposed to explain the uniformity and flatness of the observable universe, leads in some versions to a scenario known as eternal inflation, which naturally produces countless pocket universes or bubble universes within a larger inflating space. Similarly, quantum mechanics, through the many-worlds interpretation, posits that every quantum decision or observation spawns branching worlds representing different possible outcomes. These ideas do not originate from attempts to prove the multiverse. Rather, they arise organically from theoretical attempts to solve unrelated problems, and yet they all converge toward the same implication: our universe may not be alone. Another major purpose of this study is to probe the epistemological status of multiverse theories, whether they fall within the domain of science or extend beyond it into metaphysics. This question is not just technical, but philosophical in nature. Scientific theories are typically evaluated by their capacity to make falsifiable predictions and to be supported or refuted by empirical data. Critics of the multiverse argue that, because we cannot directly observe or test the existence of other universes, the hypothesis lies outside the bounds of empirical science. The study will therefore examine this boundary, exploring whether a theory that is a necessary consequence of otherwise testable and accepted models should itself be considered scientific, even if it is not directly verifiable. This work also aims to assess the potential strategies for detecting indirect evidence of the multiverse. Although we cannot observe other universes directly, some researchers have proposed that collisions or interactions between universes in the early stages of cosmic expansion might leave detectable imprints in the cosmic microwave background radiation. Other theorists suggest that if the multiverse includes regions with different physical laws, it might explain certain statistical anomalies observed in astronomical data. These ideas remain speculative, but they offer a framework for evaluating the plausibility of developing testable consequences from multiverse theories in the future. In addition to its scientific objectives, the study will investigate the philosophical and existential implications of the multiverse hypothesis. If other universes exist, potentially including versions of ourselves living different lives based on alternative outcomes of our decisions, what does this mean for our identity, our choices, and our understanding of free will? Does the existence of an infinite number of universes render our own existence meaningless? Or does it merely expand the context in which meaning is formed? These questions, while speculative, arise naturally from the premises of multiverse theories and deserve thoughtful consideration alongside the scientific discussion. Finally, the purpose of this study includes contributing to a broader scientific literacy surrounding complex theoretical topics. The multiverse, while increasingly mentioned in popular media and scientific discourse, is often misunderstood or oversimplified. By presenting a structured, balanced, and in-depth examination of the concept from multiple perspectives, this project seeks to clarify common misconceptions and to offer an accessible yet rigorous account of one of the most intriguing ideas in modern science. Whether the multiverse is ultimately proven to exist or not, its study pushes the boundaries of human knowledge and challenges us to reconsider the nature of reality itself. In summary, the goals of this study can be outlined as follows: to define and contextualize the concept of the multiverse, to explore the theoretical motivations behind it, to assess its consistency with current physical theories, to examine its implications for science, philosophy, and society, and to consider the limits and possibilities of investigating phenomena that may lie beyond empirical reach. Through these objectives, The project aims to deepen our understanding of the universe, or multiverse, we inhabit, and to reflect on the limits of what we can know about existence. The hypothesis at the heart of this study is that the multiverse exists, not merely as a speculative idea or imaginative concept, but as a theoretical consequence of established scientific models. This hypothesis does not claim definitive proof of other universes, but asserts that the existence of a multiverse is a plausible inference from multiple independent developments in modern physics. It proposes that various branches of scientific inquiry, when pushed to their logical conclusions, converge on the idea that our universe may be one among many. The aim is not to treat this as a settled fact, but to explore the grounds on which such a claim can be meaningfully formulated and investigated within the framework of scientific reasoning. The multiverse hypothesis rests on several key theoretical pillars, each of which supports the idea in a different but complementary way. The first is cosmic inflation, a well-supported model that describes an exponential expansion of the universe in its earliest moments. Inflation was originally introduced to explain certain features of the observable universe, such as its large-scale homogeneity and flatness. However, extended versions of this theory, particularly the model known as eternal inflation, predict that inflation never completely ends but continues in different regions of space. This results in a constantly branching structure where countless bubble universes emerge, each potentially with its own unique physical constants and laws. If eternal inflation is correct, then the multiverse is not a speculative addition to the theory, but a natural consequence of its core assumptions. A second pillar is the many-worlds interpretation of quantum mechanics, first proposed by Hugh Everett in the 1950s. This interpretation suggests that every quantum event with multiple possible outcomes leads to a branching of the universe into separate realities, each corresponding to a different outcome. In this framework, there is no collapse of the wave function. Rather, all outcomes exist simultaneously in separate, non-interacting branches. While this interpretation remains controversial, it has gained traction among physicists who seek a deterministic and elegant understanding of quantum phenomena. If many worlds is correct, then the universe is constantly branching into an ever-expanding tree of possibilities, with each branch constituting a separate universe in the multiverse. Another support for the hypothesis comes from string theory and its extensions, such as M-theory. String theory attempts to unify all fundamental forces and particles by modeling them as vibrating strings in higher dimensional space. One of the unexpected results of string theory is the existence of an enormous landscape of possible solutions, each corresponding to a different set of physical laws. These solutions could manifest as separate universes within a vast multiverse. According to some estimates, there may be on the order of 10 to the power of 500 such solutions, each representing a different vacuum state with its own properties. The sheer number of possible configurations makes it statistically plausible that many, perhaps infinite, other universes exist. The hypothesis also addresses philosophical questions related to fine-tuning. Our universe appears to be remarkably well suited for the emergence of life. The fundamental constants and initial conditions are so precisely arranged that even minor deviations could have resulted in a sterile cosmos. The multiverse hypothesis offers a potential explanation. If countless universes exist, each with different properties, then it is not surprising that at least one of them, ours, has the conditions necessary for life. This anthropic reasoning does not explain why the multiverse exists, but it does provide a framework for understanding why our particular universe appears so finely tuned. An important part of the hypothesis is its compatibility with known science. None of the above theories were initially developed to support the multiverse concept. They emerged independently from efforts to resolve specific problems in cosmology and quantum mechanics. That they all point, in their extended forms, to the existence of multiple universes suggests a convergent line of reasoning. The hypothesis proposes that this convergence is not accidental but reflects a deeper truth about the structure of reality. Of course, the hypothesis acknowledges its limitations. It cannot currently be tested or confirmed through direct observation, and it challenges traditional definitions of what constitutes a scientific theory. However, it asserts that indirect support may be possible. For example, certain patterns in the cosmic microwave background radiation might hint at interactions between our universe and others. In quantum physics, future developments in quantum computing or experiments on quantum decoherence might lend support to the many worlds framework. While such evidence would be circumstantial, it could strengthen the case for the hypothesis over time. The multiverse hypothesis also invites a reconsideration of what it means to explain something scientifically. Traditional scientific explanations often seek simplicity and parsimony, favoring theories that make precise, testable predictions. Yet the universe may not conform to our preferences for simplicity. If the multiverse is real, it may represent the most natural or inevitable outcome of the physical laws we are beginning to uncover. In this sense, the hypothesis is not a rejection of science, but an extension of its logic to its farthest reaches. The hypothesis is further supported by computational models and mathematical frameworks that attempt to simulate various cosmological scenarios. Advanced computer simulations of eternal inflation or quantum branching illustrate how complex and diverse multiversal structures might arise. These simulations, though still limited in scope, help visualize the otherwise abstract implications of the theories and provide a sandbox for exploring the conditions under which universes could form and evolve. In proposing the multiverse hypothesis, this study does not claim to have proven its truth. Rather, it treats the hypothesis as a serious theoretical possibility, grounded in respected branches of physics and deserving of careful exploration. It is a statement about what might be the case, based on the logical implications of current models and the unresolved puzzles of cosmology. The hypothesis acts as a guiding thread through the project, shaping the questions to be asked and the criteria by which competing ideas will be evaluated. Ultimately, the hypothesis serves as a test of the openness of the scientific enterprise. It challenges researchers to consider ideas that stretch beyond direct verification and to develop new tools, both conceptual and technological, for approaching the limits of knowledge. Whether the multiverse exists or not, the act of exploring the hypothesis can yield valuable insights into the nature of scientific explanation, the architecture of physical law, and the human drive to understand the totality of existence. The relevance of the multiverse hypothesis extends beyond theoretical physics into the broader domains of cosmology, philosophy, scientific methodology, and even human culture. This relevance lies in the transformative implications the hypothesis carries for our understanding of the universe, our place within it, and the fundamental nature of reality itself. As science progresses, it constantly reshapes humanity's conception of existence. The multiverse theory, if validated or even seriously engaged with, may represent one of the most profound paradigm shifts in the history of human thought. Comparable to the Copernican revolution, the theory of evolution, or the discovery of relativity. It invites us to reimagine the boundaries of the cosmos and challenges us to expand the scope of scientific inquiry to include possibilities that once seemed philosophical or metaphysical in nature. One of the primary reasons the multiverse hypothesis is relevant to modern science is because it emerges naturally from established theories that already explain much of what we observe. The notion is not a product of unfounded speculation. Rather, It is a logical extension of key developments in physics. Theories such as cosmic inflation, string theory, and quantum mechanics have earned credibility through their capacity to explain observable phenomena. The fact that these theories, in their most developed forms, point toward the existence of multiple universes gives weight to the hypothesis. This connection grants the multiverse conceptual legitimacy, making it a necessary area of study for physicists who take the implications of their own theories seriously. Furthermore, the relevance of the multiverse lies in its potential to answer long-standing questions that have puzzled scientists and philosophers alike. One such question involves the fine-tuning of the universe. The conditions that make life possible are so specific and precise that they defy simple probabilistic explanation. Why does the universe appear to be finely adjusted to allow the emergence of life and consciousness? In a single universe model, this fine-tuning is difficult to account for without appealing to design or coincidence. The multiverse offers a compelling alternative. If a near-infinite number of universes exist, each with different initial conditions and physical constants, then it is not surprising that we find ourselves in one where the conditions are just right. From this perspective, the multiverse not only makes sense of fine-tuning, but reframes it as an expected consequence of cosmic plurality. The relevance also reaches into the epistemological foundations of science itself. The multiverse hypothesis challenges the traditional criterion of falsifiability, an idea made central by philosopher Karl Popper. Critics often argue that because we cannot observe or test other universes, the hypothesis is unscientific. However, this critique raises deeper questions. Is falsifiability an absolute requirement? Or are there exceptions when a theory is an inevitable consequence of models that are otherwise testable? Many physicists argue that if a theory is derived from a broader framework that has been empirically confirmed, then its implications, even if untestable, should be given serious consideration. In this sense, the multiverse becomes a case study in how the methodology of science may need to evolve when dealing with phenomena at the edge of observability. Another dimension of the hypothesis's relevance is its potential to unify seemingly disparate fields of scientific research. The multiverse intersects with quantum theory, cosmology, particle physics, and information theory. Studying it requires synthesizing knowledge from multiple disciplines, fostering a kind of intellectual cross-pollination that has historically led to major breakthroughs. For example, the convergence of general relativity and quantum mechanics has long been a goal of theoretical physics, and the multiverse, especially in the context of string theory, forces researchers to consider how these two foundational pillars interact in extreme conditions. The search for a theory of everything may not be complete without reckoning with the possibility that our universe is only one node in a vast, interconnected structure of universes. Beyond the scientific domain, the relevance of the multiverse touches on human psychology and cultural imagination. The idea that there might be countless other universes, possibly containing versions of ourselves living different lives, stirs deep existential and emotional responses. It forces us to confront questions about identity, destiny, and the uniqueness of our experiences. Are we special? Is our universe meaningful, or just one of many? These questions are not merely academic. They resonate with age-old human concerns about purpose, choice, and the nature of existence. In literature, film, and art, the multiverse has become a rich metaphor for exploring such issues, showing that the hypothesis, even in its speculative form, has cultural and philosophical impact. Moreover, the relevance of multiverse research extends to technological and conceptual innovation. In attempting to explore and describe these vast and diverse universes, scientists must develop new mathematical tools, computational techniques, and even new languages of description. This pursuit pushes the boundaries of current scientific instrumentation and simulation capabilities. For instance, simulating quantum systems on a cosmological scale or modeling the behavior of universes within the framework of string theory demands advances in both hardware and theoretical frameworks. These advances, even if they never detect another universe, could yield practical applications in fields such as quantum computing, complex systems modeling, and artificial intelligence. The multiverse is also relevant in educational contexts, especially when teaching advanced students the frontiers of modern science. Introducing learners to this concept encourages them to think beyond the limits of current empirical data and to engage with the logical implications of well-established theories. It trains them to critically evaluate scientific claims, to understand the importance of philosophical rigor in science, and to appreciate the creativity inherent in theoretical physics. In doing so, the multiverse becomes a pedagogical tool, an entry point into the most profound and challenging questions science can ask. Finally, the relevance of the multiverse hypothesis is found in its capacity to redefine how humanity views its place in the cosmos. Throughout history, scientific discoveries have successively displaced humans from the center of the universe. First with the Copernican revolution, then with Darwinian evolution, and later with the realization that the Earth is an ordinary planet in an ordinary galaxy. The multiverse continues this trajectory. If our entire universe is just one among many, then even our cosmic environment loses its claim to uniqueness. This can be a humbling realization, but also an inspiring one. It suggests that the cosmos is far vaster, more mysterious, and more creative than we had ever imagined. In conclusion, the relevance of the multiverse hypothesis is multidimensional. It is grounded in scientific theory, driven by unresolved questions, challenged by philosophical scrutiny, enriched by cultural expression, and powered by human curiosity. Whether or not the multiverse is ultimately confirmed or remains a theoretical possibility, its study deepens our understanding of the universe we do inhabit, sharpens our scientific methodologies, and broadens our imagination of what reality might include. It stands as a symbol of science at its most ambitious, reaching not only to the edges of space and time, but to the very limits of what can be known. The history of the multiverse concept is rich, layered, and spans both scientific and philosophical traditions. While the term multiverse is relatively modern, the underlying idea that there may be multiple worlds or realities beyond our own can be traced back to ancient philosophical systems, theological interpretations, and early cosmological theories. Over time, as our understanding of the universe matured through advancements in astronomy and physics, the notion evolved from abstract speculation into a serious scientific hypothesis. This section explores how the idea of the multiverse developed historically, tracking its transformation from myth and metaphysics to a subject of rigorous theoretical investigation. The earliest expressions of the multiverse concept can be found in ancient philosophical traditions. In ancient Greece, the atomist philosophers Leucippus and Democritus proposed a universe composed of indivisible particles moving through the void. They imagined an infinite cosmos with countless worlds formed by the random motion and collision of atoms. According to their philosophy, these worlds could vary widely in size, structure, and content. Some could resemble our own, while others could be entirely alien. Although this idea was metaphysical and lacked empirical foundation, it marked a significant early moment in the intellectual history of cosmic plurality. Similar notions appear in early Hindu cosmology, particularly within the Vedic and Puranic texts. These writings describe an infinite cycle of universes, each undergoing creation, preservation, and destruction. Universes emerge from divine energy, evolve over vast spans of time, and eventually collapse, only to be born again. Some interpretations suggest that multiple universes exist simultaneously in an eternal cosmic ocean. This cyclical and pluralistic view of reality reflects a deep intuition that our universe may not be singular or static, but one of many within a dynamic and infinite system. The concept of a plurality of worlds also found a place in medieval Islamic and Christian philosophical discourse. Some Muslim scholars, such as Fakhr al-Din al-Razi in the 12th century, questioned the assumption that God had created only one world. Al-Razi argued that divine power was not limited and could therefore produce infinite worlds. Although not framed in scientific terms, this theological argument anticipated some of the later questions raised by modern cosmology about the uniqueness or non-uniqueness of our universe. The rise of modern science in the 16th and 17th centuries brought a radical transformation in cosmological thinking. With the Copernican revolution, Earth lost its privileged position at the center of the cosmos. Galileo's telescopic observations, Newton's laws of motion, and Kepler's planetary laws all contributed to a new vision of the universe as governed by universal laws rather than spiritual or mystical forces. This shift laid the groundwork for considering other worlds not just as abstract possibilities, but as physical entities governed by the same rules as our own. The development of Newtonian mechanics made it conceivable that distant regions of space could host planetary systems and perhaps even life. By the 18th and 19th centuries, speculation about extraterrestrial life and habitable planets grew, particularly during the Enlightenment. Philosophers and scientists such as Giordano Bruno advocated for an infinite universe filled with countless stars and worlds. Bruno argued that the same divine principle that had created Earth must have also created other inhabited worlds, each with its own life and civilizations. His ideas, although visionary, led to his persecution and execution by the Catholic Church. In retrospect, Bruno can be seen as an early prophet of the multiverse idea, even if his conception was more poetic than scientific. The 20th century brought the multiverse concept into the realm of mathematical physics and empirical science. The first major turning point came with the formulation of quantum mechanics in the 1920s. This new theory introduced indeterminacy and probability into the foundations of physics. While the Copenhagen interpretation suggested that quantum outcomes were determined by measurement, Hugh Everett's 1957 many-worlds interpretation proposed a radically different view. All possible outcomes of a quantum event actually occur, each in a separate, branching universe. According to Everett, the universe splits into different versions of itself every time a quantum event with multiple possible outcomes takes place. This idea was initially marginalized, but gradually gained traction among physicists seeking deterministic alternatives to the standard interpretation. In parallel, developments in cosmology also began to hint at a much larger reality than previously imagined. The discovery of the cosmic microwave background radiation in 1965 confirmed the Big Bang model, which described the universe as having evolved from a hot, dense initial state. In the 1980s, physicist Alan Guth proposed the theory of cosmic inflation to explain several perplexing features of the early universe, such as its large-scale homogeneity and flatness. Shortly thereafter, Andre Linde and others expanded on this idea, proposing the model of eternal inflation, where inflation never ends uniformly but continues in different regions of space. Each region where inflation stops gives birth to a pocket universe with its own distinct properties. This model marked one of the first serious attempts in modern physics to describe a mechanism that could naturally produce multiple universes. The 1990s and early 2000s saw the rise of string theory as a candidate for a unified theory of physics. String theory posits that all particles are tiny vibrating strings, and the theory requires additional spatial dimensions for mathematical consistency. It was soon discovered that string theory allows for a vast number of possible vacuum states, each corresponding to a different set of physical laws. This landscape of solutions suggested that a multiverse of universes with different physical parameters might exist. The idea gained further credibility as physicists tried to explain why our universe's physical constants appear so finely tuned for life. In this context, the multiverse provided an elegant, though controversial, explanatory framework. In the 21st century, interest in the multiverse has only deepened. Research in theoretical physics, particularly in quantum gravity and cosmological simulations, continues to explore how multiversal structures might form. Popular science books, academic papers, and public lectures have brought the concept into mainstream awareness. While debate remains intense, especially regarding the testability of the hypothesis, the multiverse is now considered a serious area of inquiry within the scientific community. The historical journey of the multiverse concept illustrates a gradual but profound evolution. From mythic visions and philosophical speculation to mathematical modeling and physical theory, the idea has traveled far. It reflects humanity's persistent desire to understand the full extent of reality, to explain why the universe is the way it is, and to grapple with the possibility that what we observe is only a small part of a vastly greater whole. As science continues to push the boundaries of the observable and the conceivable, the multiverse remains one of the most intriguing and ambitious ideas ever conceived, a testament to the depth and audacity of human thought. The multiverse, as a theoretical construct, can be defined as a collection of multiple, possibly infinite, universes that exist independently of each other. These universes may differ in a variety of fundamental ways, such as in their physical laws, constants, dimensions, or even the underlying structure of space and time. While in everyday language the word universe refers to all that exists, within scientific and philosophical discussions of the multiverse, universe is redefined to mean one causally connected region of space-time, our observable cosmos being only one of potentially many. The broader multiverse would then be the ensemble of all such universes, together forming a grander and more expansive reality. The multiverse is not a singular concept, but rather an umbrella term for a range of models that predict or allow for multiple universes. These models vary in scope and in their assumptions about the properties of each universe and the nature of their relationships, if any, to each other. In some cases, universes within a multiverse are entirely separate, never interacting in any meaningful way. In others, they may exist within a larger geometric framework that occasionally allows for collisions, overlaps, or observable traces. The term multiverse therefore encompasses a wide array of ideas and must be understood as a conceptual space rather than a single, unified theory. At its most basic, the multiverse hypothesis arises from the recognition that there might be more to reality than what is observable from within our own cosmic horizon. This idea gains strength when one considers that the observable universe is limited not by the extent of space itself, but by the speed of light and the age of the cosmos. There may be regions so distant that light from them has not yet reached us, and perhaps never will due to the accelerating expansion of space. Some physicists argue that these faraway regions, though currently beyond our observational capabilities, are part of the same space-time fabric and thus not other universes in a strict sense. Others contend that if those regions have different properties or histories, they may be functionally or even ontologically distinct, making the term universe appropriate for each. Defining the multiverse also requires us to examine the nature of the physical laws that govern our universe. Are these laws universal in the absolute sense, or could they be local expressions of a deeper, more general framework? In many multiverse models, each universe operates under its own set of physical laws and constants. In this view, what we call laws of physics may be contingent rather than necessary, specific to our universe, but not shared across all possible universes. This redefinition challenges a long-standing assumption in science that there is a single, immutable set of laws governing all of reality. In cosmology, the multiverse is often discussed in relation to inflationary theory. According to the model of eternal inflation, the rapid exponential expansion of the early universe continues in some regions, creating a never-ending process of universe creation. Each bubble that forms when inflation ends constitutes a separate universe with potentially unique characteristics. These universes are causally disconnected from one another, embedded in a larger inflating space that is itself unobservable. This framework gives rise to a form of multiverse that is spatially infinite and physically diverse, with the ensemble potentially containing every possible configuration of matter and energy. In quantum mechanics, the idea of the multiverse emerges from the many-worlds interpretation (MWI), which posits that all possible outcomes of a quantum event occur, each in its own branch of reality. In this model, the universe constantly splits into parallel versions of itself as quantum events unfold. These parallel universes coexist, but are decoherent from one another, meaning they do not interact or influence each other after branching. This type of multiverse is not spatial in the same way as the cosmological one. It is more abstract, arising from the mathematical structure of quantum mechanics rather than from geometric expansion or spatial separation. Another form of multiverse is suggested by string theory, particularly through the concept of the string landscape. String theory allows for a vast number of vacuum states, each representing a different way the extra dimensions could be compactified. These different compactifications result in different low-energy physics, that is, different observable laws and constants. The landscape of solutions implies the existence of a vast number of physically distinct universes, each corresponding to a particular point in this mathematical space. If realized physically, this string landscape could represent a multiverse composed of universes with entirely different particle content, forces, and structures. Still more abstract is the mathematical multiverse proposed by physicist Max Tegmark, which posits that all mathematically consistent structures exist physically. In this view, any universe that can be described by a self-consistent set of mathematical rules exists somewhere in the total multiverse. This Level 4 multiverse transcends physical models and includes realities that may be utterly unlike our own, not only in their laws, but in their dimensionality, logic, and fundamental structures. It is the broadest and most speculative conception of the multiverse, but also the most logically exhaustive. An important element in defining the multiverse is the question of accessibility. Are these other universes forever out of our observational reach, or could some form of indirect evidence support their existence? This question divides multiverse models into different categories based on their degree of empirical engagement. Some propose observational signatures, such as patterns in the cosmic microwave background, that might hint at collisions between universes. Others, like the quantum and mathematical multiverses, seem to resist observational confirmation altogether, remaining in the realm of inferred possibility rather than detectable reality. Despite their differences, all multiverse models share a common implication: that the reality we experience is only a small part of a much larger totality. This has profound consequences not only for physics, but for metaphysics, epistemology, and even ethics. If other versions of ourselves exist, does this alter the meaning of choice, responsibility, or identity? If the universe is just one among countless others, does this change how we assign significance to our place in the cosmos? Defining the multiverse, therefore, involves not only scientific language, but also philosophical reflection on what it means for something to exist, to be real, and to be knowable. In sum, the multiverse is a complex and multifaceted idea that resists a single, definitive definition. It encompasses a variety of models and interpretations, each with its own assumptions and implications. While not yet part of the empirical core of physics, it has become a powerful theoretical framework for exploring the limits of our understanding. Whether as a cosmological structure, a quantum consequence, a string-theoretic necessity, or a mathematical totality, the multiverse challenges us to reconsider the nature of the universe and of reality itself. The classification of multiverse types is a crucial step in understanding the various theoretical frameworks that give rise to the concept. Not all multiverse models are created equal. They originate from distinct branches of physics and mathematics and make different assumptions about the nature of reality, causality, and physical law. One of the most influential attempts to categorize multiverses comes from cosmologist Max Tegmark, who proposed a taxonomy of 4 levels of multiverse, each representing a progressively more radical departure from our familiar understanding of space, time, and physics. These categories provide a useful way to organize and compare the many multiverse theories that have emerged in contemporary science. The first type, known as the Level 1 multiverse, is the least controversial and requires no exotic physics beyond what we already understand. It emerges directly from the cosmological principle and the theory of inflation. According to this model, space is infinite, or at least so vast that it might as well be infinite, and within it, regions exist that are so far apart that they are causally disconnected from us. Because the speed of light is finite and the universe is only about 13.8 billion years old, we can observe only a limited region, the observable universe. Beyond this cosmic horizon, however, there may be countless other regions that resemble our own in structure and composition. These regions are governed by the same laws of physics, but have different initial conditions, meaning that particles and galaxies are arranged differently. In this view, another Earth-like planet, or even an exact copy of yourself, could exist in a distant region of space, provided there is enough room for all possible configurations to occur. This type of multiverse does not challenge the foundations of physics. It is a simple extension of what we already know about the structure of space-time. The Level 2 multiverse takes the idea further by suggesting that the physical constants and laws themselves can vary between universes. This concept arises from eternal inflation and the string theory landscape. In this model, inflation is not a one-time event, but an ongoing process that occurs in different regions of space-time, each producing a distinct bubble universe. Within each bubble, inflation ends, and the universe evolves according to the specific vacuum state that dominates that region. Because the string theory landscape allows for a vast number of different vacuum states, each corresponding to a unique set of physical laws and constants, the Level 2 multiverse consists of universes that are fundamentally different from one another, not just in arrangement of matter, but in the very rules that govern matter and energy. One universe may have a strong nuclear force that binds atoms tightly, while another may lack stable elements altogether. Our universe, in this framework, is one bubble among many in a vast inflating sea, and it happens to have the properties necessary for life to emerge. The Level 3 multiverse comes from the realm of quantum mechanics and is based on the many-worlds interpretation (WI) proposed by Hugh Everett. In standard quantum mechanics, particles exist in a superposition of states until they are observed, at which point the wave function collapses into a definite state. The MWI rejects wave function collapse entirely and instead posits that all possible outcomes of a quantum event actually occur, each in its own separate, non-communicating branch of reality. In this model, every quantum measurement causes the universe to split into multiple versions of itself, each representing a different result. These parallel universes are not spatially separated like in level 1 or 2, but they occupy the same space-time in a superpositional sense. They are causally isolated from one another after branching and evolve independently. While this model may seem strange, it preserves the deterministic evolution of the wave function and avoids the need for arbitrary collapse postulates. The Level 3 multiverse is perhaps the most philosophically provocative, as it implies that every decision you make creates multiple versions of you, each living out a different possibility. The Level 4 multiverse is the most abstract and speculative of Tegmark's categories. It posits that all mathematically consistent structures exist as physical realities. In other words, any system that can be described by a self-consistent set of mathematical rules corresponds to a real universe. This is based on the mathematical universe hypothesis, which holds that mathematics is not just a language we use to describe reality, but that reality itself is a mathematical structure. In this view, our universe is just one among an infinite variety of mathematical structures, each realized in its own domain. The implications are vast and difficult to fully comprehend. Some of these universes might contain different numbers of dimensions, different types of logic, or even fundamentally alien structures that are impossible to visualize. The Level 4 multiverse effectively removes any special status from our universe, suggesting that existence itself is a broader category than physics traditionally allows. In addition to Tegmark's framework, other classifications have been proposed based on different criteria. Some models are built on modifications of general relativity, others arise from black hole cosmology, and still others are tied to computational theories of the universe. For example, in black hole cosmology, it has been proposed that every black hole might contain a new universe on the other side of its event horizon. In these models, the birth of a universe is linked to the death of a star in a parent universe, creating a kind of generational chain of universes, each potentially with its own set of laws and properties. Another category includes brain-world models derived from string theory, in which our universe is a three-dimensional membrane, brain, embedded in a higher dimensional space. Other brains may exist parallel to ours in this higher dimensional bulk, possibly interacting under certain conditions. Such interactions could, in theory, produce observable effects, like gravitational anomalies or collisions between universes, leaving imprints in the cosmic microwave background. The diversity of multiverse models reflects the richness of modern theoretical physics and the multitude of questions it seeks to answer. Some of these models are mutually compatible. For example, Level 1 and Level 2 multiverses may coexist within an inflationary framework. Others are based on entirely different assumptions and are therefore logically independent. This variety makes it challenging to discuss the multiverse as a single concept, but it also opens the door to a wide range of testable ideas and philosophical interpretations. Despite their differences, all multiverse types share a common theme. They expand our conception of reality beyond the visible, beyond the local, and beyond the familiar. They challenge the notion that the universe we observe is all that exists and invite us to consider that our cosmic neighborhood might be part of a much larger, more complex, and more mysterious totality. By classifying and studying these different types, we can better understand the scope of modern cosmology, the implications of our best physical theories, and the profound questions that arise when we ask whether this universe is the only one. The idea of the multiverse is deeply intertwined with string theory, one of the most ambitious and mathematically complex frameworks in theoretical physics. String theory attempts to unify all known forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, into a single theoretical structure. At its core, string theory proposes that the fundamental building blocks of the universe are not point-like particles, as suggested by the standard model of particle physics, but rather one-dimensional objects called strings that vibrate at specific frequencies. Each vibration mode corresponds to a different particle, much like different vibrations of a violin string produce different musical notes. The connection between string theory and the multiverse becomes apparent when one considers the theory's implications for the structure of the universe. Unlike traditional theories of physics, which operate in the familiar four-dimensional space-time, 3 dimensions of space and 1 of time, string theory requires additional spatial dimensions for mathematical consistency, typically 10 or 11 dimensions in total, depending on the version of the theory. These extra dimensions are not observable in everyday life because they are believed to be compactified or curled up into extremely small scales, far beyond the reach of current experimental probes. The way in which these extra dimensions are compactified plays a crucial role in determining the physical properties of a given universe. This includes the types of particles it contains, the strengths of its fundamental forces, the masses of particles, and even the value of the cosmological constant. The number of possible compactifications is staggeringly large, leading to what physicists call the string landscape. This landscape refers to the set of all possible low-energy vacuum states that can result from different ways of curling up the extra dimensions. Each vacuum state corresponds to a unique universe, with its own physical laws and constants. In this framework, the multiverse is not just a possibility. It may be a natural consequence of string theory. If the landscape of possible vacuum states is real, and if physical processes such as eternal inflation can sample these states by producing new universes through quantum fluctuations, then the multiverse becomes a necessary implication of the theory. In this scenario, our universe is just one bubble among an inconceivable number of others, each representing a different point in the string landscape. Some of these universes may resemble ours, while others could be completely alien, with different numbers of dimensions, different types of matter, and different governing equations. The mechanism by which these multiple universes arise is often linked to the theory of eternal inflation. Inflation is a period of extremely rapid expansion believed to have occurred in the first fractions of a second after the Big Bang. In some models, inflation is not a singular event, but a continuing process that occurs in different regions of space-time. As inflation proceeds, it can generate bubble universes where inflation ends locally, allowing these regions to cool and form structures like galaxies and stars. Each bubble may settle into a different vacuum state on the string landscape, resulting in a multiverse of diverse universes. String theory and eternal inflation thus form a powerful theoretical alliance. Inflation provides the dynamics for creating universes, while string theory supplies the blueprint for what those universes can be like. This combination is one of the most compelling multiverse models in modern physics, and is often referred to as the string inflationary multiverse. In this picture, our universe is not fine-tuned for life by design, but simply one of many possible universes, most of which are inhospitable to life. We find ourselves in this particular universe because it has the right conditions for life to exist, a principle known as the anthropic principle. This brings us to one of the more controversial aspects of the multiverse derived from string theory, the role of anthropic reasoning. In a multiverse where all possible physical laws are realized somewhere, the question of why our universe has the properties it does becomes less about necessity and more about probability. According to the anthropic principle, We observe the universe to have life-permitting constants simply because we couldn't be here to observe it otherwise. This line of reasoning shifts the focus from seeking unique explanations for the values of physical constants to understanding the distribution of these values across the landscape and determining which values are compatible with the existence of observers. Critics argue that anthropic reasoning is unscientific because it lacks predictive power and cannot be empirically tested. Proponents counter that, in a sufficiently large multiverse, it is the only way to make sense of the apparent fine-tuning of physical parameters without invoking supernatural or non-naturalistic explanations. They argue that the multiverse provides a naturalistic context in which such fine-tuning is not surprising but inevitable. Another implication of the string multiverse is the potential inaccessibility of direct empirical evidence. If other universes are causally disconnected from ours, then we may never be able to observe them directly. This raises questions about the scientific status of string theory itself, especially when it is invoked to explain features of our universe that could otherwise seem arbitrary. Critics suggest that without testable predictions, string theory, and by extension, the multiverse it implies, falls outside the domain of empirical science. Defenders of the theory argue that while direct evidence may be elusive, indirect tests and consistency with other known physics may still support the theory's validity. Despite these debates, the connection between string theory and the multiverse has had a profound impact on theoretical physics. It has opened new avenues of research, redefined questions about the nature of physical law, and challenged traditional notions of simplicity and uniqueness in scientific explanation. It has also led to increased interest in the foundations of cosmology, the limits of scientific reasoning, and the interplay between physics and philosophy. In summary, string theory does not merely allow for the possibility of a multiverse, it may require it. Through the vast array of possible vacuum states encoded in the string landscape, combined with the dynamics of eternal inflation, the theory provides a plausible mechanism for the existence of countless universes, each with its own unique properties. While many aspects of this framework remain speculative and unproven, it represents one of the most ambitious and comprehensive attempts to understand the fundamental nature of reality. Whether the multiverse predicted by string theory will ever be confirmed or refuted remains an open question, but it continues to shape the frontiers of modern theoretical physics in profound and unexpected ways. Quantum mechanics, with its counterintuitive and probabilistic nature, plays a central role in discussions of the multiverse. At the heart of this connection lies the many-worlds interpretation (MWI), a radical, yet mathematically consistent reading of quantum theory that suggests every quantum event spawns multiple parallel realities. This interpretation not only offers a coherent framework for understanding the peculiar behavior of particles at the quantum level, but also serves as a foundation for the Level 3 multiverse. In this model, the universe continually branches into countless new versions of itself, each representing a different outcome of every quantum interaction. This concept is not just a philosophical abstraction. It is a direct implication of the standard formalism of quantum mechanics, when taken at face value. To appreciate the relationship between quantum mechanics and the multiverse, one must first understand the basics of quantum theory. Quantum mechanics describes the behavior of particles and systems at extremely small scales, atoms, electrons, photons, where classical laws of physics break down. At this level, particles do not have definite positions or velocities until they are measured. Instead, they exist in a state of superposition, described by a mathematical object called a wave function. This wave function encodes all possible outcomes of a system, each with a certain probability. When an observation is made, the wave function appears to collapse, and only one of the possible outcomes is realized. The traditional, or Copenhagen, interpretation of quantum mechanics posits that this collapse is a fundamental part of nature, that measurement somehow forces the system to choose a single reality. However, this interpretation has long been criticized for its vagueness, especially regarding the role of the observer and the mechanism of collapse. Why should observation by a conscious being cause a fundamental change in a physical system? Where exactly does the boundary between quantum superposition and classical reality lie? These questions have led to ongoing debates and dissatisfaction among physicists. Enter the many-worlds interpretation, proposed in 1957 by American physicist Hugh Everett III. Rather than invoking wave function collapse, Everett suggested that all possible outcomes of a quantum measurement actually occur, but in separate, non-interacting branches of the universe. In this view, the universe splits whenever a quantum event has multiple possible outcomes. For example, if a quantum particle has a 50% chance of being spin up and a 50% chance of being spin down, then the universe divides into two. In one, the particle is spin up. In the other, it is spin down. This process happens constantly for every quantum interaction, resulting in an unimaginably vast and ever-growing tree of realities, each representing a different history of the universe. The implications of this interpretation are profound. Every time you make a decision, whether to go left or right, whether to speak or stay silent, the universe branches, creating versions of you who made the opposite choices. These parallel versions of yourself exist in separate branches of reality and are unaware of one another. The multiverse, in this model, is not spatially distinct, like in the level 1 or 2 multiverse, but emerges from the structure of quantum theory itself. The different worlds are not located in different parts of space, but coexist in a larger Hilbert space, a mathematical structure used in quantum mechanics to describe all possible states of a system. One of the strengths of the many-worlds interpretation is that it removes the need for an arbitrary collapse postulate. The evolution of the wave function, governed by the Schrödinger equation, is smooth and deterministic. There is no sudden, mysterious change upon observation. Instead, the observer becomes entangled with the system, and both evolve together into a superposition of observer system states. In each branch, the observer perceives a single outcome, unaware of the others. From a global perspective, however, all outcomes exist simultaneously, and reality is fundamentally a vast, branching structure of intertwined possibilities. Despite its mathematical elegance, the many-worlds interpretation is not without controversy. One major objection is that it appears to violate Occam's razor, the principle that we should not multiply entities beyond necessity. Critics argue that postulating the existence of countless unobservable universes is an extravagant price to pay to preserve determinism in quantum mechanics. Others question the status of probability in the MWI. If all outcomes happen, what does it mean to say that one is more probable than another? Efforts have been made to derive the Born rule, the rule that assigns probabilities to quantum outcomes, from the structure of the multiverse itself, but this remains an area of active research and debate. Another challenge is the apparent lack of empirical evidence. Because the different branches of the multiverse are non-communicating, interference between them is quickly suppressed by a process called decoherence. We cannot access or observe them directly. This raises philosophical questions about whether the multiverse is a scientific hypothesis or a metaphysical one. Proponents argue that since the MWI is a natural extension of standard quantum mechanics and makes the same predictions for observable phenomena, it is just as legitimate as any other interpretation. Indeed, it may be more consistent, as it avoids introducing arbitrary collapse mechanisms or special roles for observers. Quantum cosmology, the application of quantum mechanics to the entire universe, further strengthens the link between quantum theory and the multiverse. In quantum cosmology, the universe itself is treated as a quantum system, described by a wave function that includes all possible configurations of space-time and matter. In this framework, the multiverse is not an optional feature. It is built into the mathematical structure of the theory. Some researchers have proposed models in which the universe tunnels through quantum barriers to spawn new universes, each with different physical parameters. These ideas connect with the concept of quantum fluctuations in the early universe, which may have seeded both the structure of our universe and the formation of others. Additionally, the phenomenon of quantum entanglement, where particles become correlated in such a way that the state of one instantly affects the state of another, no matter the distance, hints at a deeper underlying reality that transcends classical notions of locality and separability. While entanglement itself does not imply a multiverse, it supports the idea that reality at the quantum level is more interconnected and non-intuitive than previously thought. Some theorists suggest that entanglement and decoherence may help explain how classical reality emerges from the quantum multiverse, acting as a kind of selection mechanism for stable branches. In conclusion, quantum mechanics offers not only a mathematical framework for understanding the smallest components of the universe, but also a radical vision of reality in which every possibility is realized in some branch of the multiverse. The many-worlds interpretation, while controversial, provides a consistent and elegant picture that aligns closely with the formalism of quantum theory. It eliminates the need for wave function collapse and offers a natural explanation for the apparent randomness of quantum events. Whether or not the multiverse it describes is real in a physical sense remains an open question, but its implications for our understanding of identity, causality, and the nature of existence are profound. As quantum theory continues to shape the frontiers of science and philosophy, the multiverse remains one of its most fascinating and provocative consequences. Cosmological inflation, a theoretical cornerstone of modern cosmology, offers another compelling framework that supports the idea of a multiverse. Originally introduced in the early 1980s by physicist Alan Guth, inflation was developed to solve several outstanding problems in the standard Big Bang model, such as the horizon problem, the flatness problem, and the monopole problem. At its core, inflation proposes that the universe underwent an extremely rapid and exponential expansion within a tiny fraction of a second after the Big Bang, specifically from approximately 10⁻36 10⁻36, 10⁻36 to 10⁻32 10⁻32, 10⁻32 seconds after the universe's birth. During this period, space itself expanded so quickly that regions previously in close contact were pushed far apart, leading to the large, smooth, and homogeneous cosmos we observe today. One of the most intriguing extensions of the inflationary model is the concept of eternal inflation. While the original inflationary phase of our universe came to an end, allowing for the formation of matter, galaxies, and eventually life, eternal inflation suggests that inflation never truly ends everywhere. Instead, it continues in different regions of space-time indefinitely, even as it ends in local pockets. In this view, our universe is merely one such pocket, a bubble universe, in a much larger and continuously inflating space. Each bubble could have different physical conditions, depending on the dynamics of its inflationary process and the underlying fields driving it. The driving force behind inflation is typically modeled as a scalar field known as the inflatant field. The energy density of this field fuels the exponential expansion of space. In eternal inflation, quantum fluctuations in the inflatant field can cause some regions of space to inflate faster than others. These fluctuations prevent inflation from ending uniformly across the entire cosmos. Instead, As inflation ends in one region, creating a universe like ours, it continues elsewhere, and new bubbles continue to form, each becoming a separate universe with its own Big Bang, physical constants, and potentially different laws of physics. These regions are causally disconnected from each other due to the vast distances between them and the rapidity of inflation, which stretches space faster than light can travel. This makes direct interaction between universes impossible, at least by current physical understanding. The structure that arises from this process is referred to as the inflationary multiverse, or Level 2 multiverse in Max Tegmark's classification. It suggests a cosmos composed of an infinite or near-infinite collection of bubble universes, each with potentially different values for fundamental constants, particle content, and vacuum states. What makes this idea particularly powerful is its explanatory potential. The inflationary multiverse provides a naturalistic explanation for the apparent fine-tuning of physical constants in our universe. If there are countless universes, each with randomly assigned values of physical parameters, it is no longer surprising that at least one of them, ours, has the right conditions for life to exist. This use of the anthropic principle, although philosophically controversial, offers a framework for understanding why the universe seems so precisely calibrated for the emergence of complex structures and conscious observers. Moreover, inflation makes specific predictions that can be tested, even if the multiverse itself remains beyond our observational reach. For instance, the theory predicts a nearly scale-invariant spectrum of primordial density fluctuations, which has been confirmed by measurements of the cosmic microwave background (SMB) radiation, such as those taken by the Planck satellite and other observatories. These fluctuations are believed to have originated from quantum perturbations during inflation, later stretched to macroscopic scales by the rapid expansion of space. Despite these successes, eternal inflation, and by extension, the inflationary multiverse, raises deep conceptual and philosophical questions. One of the major concerns is the measure problem, which arises when attempting to make predictions in a universe with an infinite number of outcomes. In such a scenario, every possible event not only can happen, but happens an infinite number of times. This makes it difficult to define meaningful probabilities, since comparing infinities leads to ambiguous and sometimes contradictory results. Several approaches have been proposed to resolve this, including regulating the infinities by imposing cutoffs or defining probability measures in specific ways, but no consensus has emerged. Another challenge is the lack of direct observational access to other bubble universes. While our universe's inflationary past leaves imprints on the CMB, the interiors of other bubbles are beyond our horizon, making empirical confirmation of their existence difficult. Some theorists have suggested that if two bubble universes were to collide, the impact might leave a detectable signature, such as circular anomalies in the CMB. To date, no such definitive evidence has been found, though searches continue. Critics argue that the unobservable nature of other universes renders the inflationary multiverse speculative or even non-scientific. They claim that a theory which makes no falsifiable predictions about other domains of reality falls outside the boundaries of empirical science. However, proponents counter that the multiverse is not a separate theory, but a logical consequence of inflation, which is itself strongly supported by data. If eternal inflation naturally leads to a multiverse, then denying the multiverse while accepting inflation might be inconsistent. Furthermore, eternal inflation has deep connections with string theory, another major theoretical framework. In string theory, the multitude of possible vacuum states, the string landscape, provides the variety of possible physical laws that each bubble universe could realize. This synergy between string theory and inflation strengthens the theoretical foundation of the multiverse hypothesis, suggesting that different regions of the multiverse sample different parts of the landscape. There are also profound implications for cosmology and the philosophy of science. If the multiverse exists, our understanding of the universe's uniqueness, predictability, and the nature of explanation must be re-examined. Instead of a single, finely tuned cosmos, we inhabit one of many, and scientific inquiry must adapt to this broader context. Some philosophers and physicists argue that the multiverse moves science closer to historical sciences like evolutionary biology, where understanding the full ensemble, e.g., all possible species, helps explain the characteristics of one particular instance, e.g., humans. In summary, cosmological inflation, particularly in its eternal form, provides a robust and well-motivated framework that leads naturally to the idea of a multiverse. While the inflationary multiverse is not yet directly observable, its roots in well-tested physics, its explanatory power regarding fine-tuning, and its connection to broader theoretical constructs make it a leading candidate for a deeper understanding of cosmic reality. It invites us to think beyond the visible universe and consider the possibility that our cosmos is just one of many, endlessly spawning new realities in the ever-expanding tapestry of space-time. The arguments in favor of the multiverse concept stem from a variety of scientific disciplines and theoretical frameworks, each contributing pieces to a broader, if still speculative, picture of reality. These arguments do not rely solely on imaginative thought or philosophical speculation. Rather, they are grounded in well-established physical theories, logical extensions of mathematical frameworks, and attempts to explain persistent questions in cosmology and quantum mechanics. Though none of them can yet provide direct empirical confirmation, the cumulative weight of these arguments gives the multiverse hypothesis a surprising degree of scientific credibility. One of the most compelling arguments supporting the multiverse idea comes from inflationary cosmology, particularly the notion of eternal inflation. As discussed previously, if inflation is indeed eternal, then the formation of bubble universes is an inevitable consequence. Each of these bubble universes would represent a separate domain of space-time, potentially with its own unique set of physical constants and laws. Because eternal inflation arises from relatively simple and widely accepted assumptions about scalar fields and quantum fluctuations, it's difficult to discard the multiverse without rejecting inflation altogether, something few cosmologists are willing to do, given the theory's success in explaining the observed features of our universe. Another major line of support comes from quantum mechanics, especially the many-worlds interpretation. According to this interpretation, every quantum measurement results in the branching of the universe into distinct realities, each representing a different outcome. While other interpretations of quantum mechanics avoid invoking multiple worlds, none of them have successfully eliminated the observer-dependent nature of measurement or the collapse of the wave function without introducing ad hoc elements. The many-worlds interpretation, on the other hand, offers a cleaner, more consistent reading of the formalism of quantum mechanics, one that naturally leads to a vast ensemble of coexisting universes. In this sense, the multiverse is not an addition to quantum theory, but an implication of taking the mathematics seriously. The string theory landscape provides yet another powerful theoretical basis for the multiverse. String theory attempts to reconcile general relativity with quantum mechanics by positing that the fundamental constituents of reality are not particles, but tiny, vibrating strings. One of the consequences of string theory is that it allows for an enormous number, perhaps on the order of 1050010 carat 500 10500 of different vacuum solutions, each corresponding to a different way of compactifying the extra dimensions required by the theory. Each vacuum solution could, in principle, produce a universe with distinct physical laws and constants. This multitude of possible configurations forms what is known as the string landscape. If eternal inflation populates this landscape randomly, generating bubble universes with different properties, then the multiverse becomes a natural consequence of combining these two leading theories. Beyond theoretical physics, the multiverse also offers a potential solution to the long-standing puzzle of fine-tuning. Observations indicate that many of the fundamental constants of nature, such as the strength of the electromagnetic force, the masses of elementary particles, or the cosmological constant, appear to be exquisitely tuned to allow the existence of complex structures, stars, planets, and life. Even small deviations in these parameters could render the universe sterile or short-lived. While some physicists have attempted to find a theory of everything that uniquely determines all these constants, progress has been slow and inconclusive. The multiverse offers an alternative explanation. If there are vast numbers of universes with different constants, it's not surprising that at least one of them, ours, has the right conditions for life. This use of the anthropic principle may be unsatisfying to some, but it provides a logically coherent and scientifically grounded response to an otherwise baffling question. Further support for the multiverse idea comes from certain areas of mathematics and logic. Some thinkers, such as Max Tegmark, have proposed the existence of a level 4 multiverse, in which all mathematically consistent structures have physical existence. According to this view, reality is not just described by mathematics, it is mathematics. Every possible mathematical universe exists, whether or not it is observable from our own. Though this view ventures into metaphysical territory, it builds on the surprising effectiveness of mathematics in describing the physical world. The fact that abstract equations can so precisely model real phenomena suggests that the relationship between mathematics and reality might be deeper than traditionally assumed. There are also arguments based on symmetry and simplicity. Many physical theories are guided by the principle that the laws of nature should not contain unnecessary complexity or arbitrary features. In some ways, the multiverse offers a simpler picture of reality, not in terms of intuitive understanding, but in terms of theoretical elegance. Instead of trying to explain why our universe has a particular set of parameters, the multiverse accepts that all possible combinations exist, and our universe is simply one of them. In this sense, the multiverse can be seen as reducing the burden of explanation, rather than requiring a unique and possibly contrived mechanism to generate one specific universe. It accepts the diversity of all. A growing number of simulations and computational models also lend indirect support to the plausibility of multiverse scenarios. In certain simulations of inflationary dynamics, bubble universes appear spontaneously under a wide range of initial conditions. Likewise, models based on cellular automata or other algorithmic processes show that complex structures can emerge from simple, rule-based systems with a large enough parameter space, mirroring the variety expected in a multiverse. While these simulations cannot prove the existence of other universes, they demonstrate that such outcomes are natural and robust within certain mathematical frameworks. In recent years, some physicists have even begun to explore the possibility of observable evidence for the multiverse. Although bubble universes are typically separated by vast distances and cannot interact, in some scenarios, their formation could lead to collisions that leave detectable imprints in the cosmic microwave background. These signatures might take the form of circular patterns, anomalies in temperature fluctuations, or unexpected alignments. While no such patterns have been definitively confirmed, the search continues using increasingly sensitive instruments and data analysis techniques. Additionally, certain theories predicting the multiverse make indirect predictions that can be tested. For example, the statistical distribution of physical constants in a multiverse might imply that certain values are more likely than others, If we observe that our universe's constants lie near the edge of the anthropically allowed range, that would be consistent with the idea that we are typical observers in a multiverse, rather than inhabitants of a uniquely fine-tuned cosmos. These kinds of Bayesian or statistical tests are controversial, but represent an effort to bring the multiverse into the realm of scientific discourse. To be sure, the multiverse remains a highly speculative hypothesis, and many physicists caution against embracing it too quickly or too enthusiastically. Nonetheless, the cumulative force of these arguments, from cosmology, quantum theory, string theory, mathematics, and observational cosmology, has moved the idea from the fringes of science to a topic of serious discussion and active research. As our understanding of the universe deepens, the multiverse offers not just a possibility, but perhaps an inevitability, that reality is far richer, more complex, and more surprising than we ever imagined. While the multiverse hypothesis has gained considerable traction in theoretical physics, it is by no means without its critics. A range of arguments have been raised against the idea, many of them highlighting serious philosophical, methodological, and scientific concerns. These criticisms challenge not only the internal logic of multiverse theories, but also their compatibility with the principles of empirical science. To fully understand the status of the multiverse in contemporary thought, it is crucial to consider these counterarguments and the dilemmas they present. One of the most persistent objections is the problem of falsifiability. Science is traditionally distinguished from other forms of inquiry by its reliance on empirical evidence and the principle that theories must be testable and falsifiable. In other words, a scientific claim should be vulnerable to disproof by observation or experiment. The multiverse, by its very nature, seems to violate this criterion. If other universes are causally disconnected from ours, beyond the limits of observational reach, then how could we ever obtain evidence of their existence? Without a way to confirm or refute the presence of other universes, critics argue, the multiverse remains a metaphysical speculation rather than a scientific theory. This issue has sparked an intense debate within the philosophy of science. Some scientists and philosophers argue that we may need to revise our definition of scientific validity, especially when dealing with theories at the frontiers of knowledge, such as cosmology and fundamental physics. Others maintain that no theory should be accepted as scientific unless it makes clear, testable predictions. The tension here is not just academic. It cuts to the heart of what we consider meaningful scientific discourse. If the multiverse is allowed into the fold despite its untestability, what prevents any number of speculative ideas from claiming scientific status? A related concern is the measure problem, which emerges in the context of the inflationary multiverse. If there are infinitely many universes, each containing observers like us, how do we assign probabilities to events? For instance, if every possible outcome happens somewhere, how do we say what is likely or unlikely within the multiverse? This makes statistical reasoning problematic and undermines one of the core tools scientists use to make sense of data. Several different measures have been proposed to tame the infinities and provide a coherent framework for calculating probabilities, but no consensus has emerged, and some measures lead to paradoxical results. Another criticism is that the multiverse may represent a kind of scientific surrender. Rather than explaining why our universe has the properties it does, multiverse theories often invoke the anthropic principle. We observe a universe compatible with life simply because we exist in it. While logically sound, this reasoning can be seen as a way to avoid deeper investigation. Instead of striving to find a unique, predictive theory of fundamental physics, the multiverse approach might encourage a view in which anything is possible and nothing is ultimately explainable. Detractors worry that this could erode the explanatory power of science itself and reduce it to a catalog of observations with no underlying necessity. Furthermore, some critics argue that the multiverse hypothesis violates Occam's razor, the principle that among competing hypotheses, the one with the fewest assumptions should be preferred. Invoking an infinite number of unobservable universes to explain the properties of one observable universe seems, to some, like an extravagant multiplication of entities. While multiverse proponents counter that the hypothesis may actually be simpler in terms of theoretical structure, arising naturally from inflation, string theory, or quantum mechanics, skeptics remain unconvinced that this justifies such a radical ontological commitment. There are also philosophical and existential implications of the multiverse that trouble some observers. If there are infinite versions of every possible reality, what does that mean for individual identity, morality, or the uniqueness of human experience? In a multiverse where all outcomes occur, does personal choice lose meaning? Are we just one of countless copies scattered across infinite space-time branches? These questions are not strictly scientific, but they influence how people interpret the plausibility and implications of the theory. The idea that our lives are just one of infinite variations can feel destabilizing or even nihilistic to some, while others may find it liberating or awe-inspiring. Another area of concern is that many versions of the multiverse are extremely sensitive to theoretical assumptions that have not been confirmed by experiment. For example, eternal inflation depends on the existence and behavior of scalar fields, such as the inflaton, which remain hypothetical. Similarly, the string landscape presumes a particular formulation of string theory, a framework that itself has not been empirically verified and faces significant challenges in making concrete predictions. Critics argue that until these underlying theories are better substantiated, any conclusions drawn from them, including the existence of a multiverse, are premature. It is also worth noting that empirical alternatives to the multiverse explanation for fine-tuning may exist. Some physicists continue to search for a theory of everything that would determine the values of all physical constants from first principles, eliminating the need for anthropic reasoning or multiple universes. If such a theory were found, it could explain the apparent fine-tuning without invoking the existence of a multiverse. Until this effort is exhausted, some argue, the multiverse should be considered a fallback position rather than a primary explanation. Even within the community of physicists who take the multiverse idea seriously, there is significant disagreement about its implications and proper role in science. Some view it as a testable extension of existing theories, while others see it as a placeholder for future insights. There are ongoing efforts to find indirect signatures of other universes, such as anomalies in the cosmic microwave background that might indicate past collisions between bubble universes, but so far, no conclusive evidence has emerged. The lack of consensus reflects both the novelty of the idea and the limits of our current observational tools. In sum, the criticisms of the multiverse are not trivial objections, but deep challenges that demand careful consideration. They highlight fundamental tensions in how science is practiced and understood, especially at the boundaries of knowledge. While multiverse theories may offer elegant solutions to certain problems, they also raise new ones: epistemological, methodological, and philosophical. Whether the multiverse proves to be a legitimate scientific hypothesis, a useful conceptual framework, or a misguided detour remains to be seen. What is clear, however, is that grappling with these objections is essential for any honest appraisal of the idea and for the continuing evolution of our understanding of the universe. The question of whether the multiverse can be confirmed or supported through empirical evidence is one of the most pressing and contentious in theoretical physics today. While many multiverse models are grounded in serious mathematical frameworks and emerge naturally from accepted theories like inflation and quantum mechanics, they often seem to escape the traditional bounds of testability. Yet the scientific community has not entirely given up hope. Instead, researchers are exploring creative and often indirect ways to assess whether the multiverse leaves any observable traces, or if it ever could. One of the most discussed possibilities for testing the multiverse comes from the idea of bubble collisions in the context of eternal inflation. In this scenario, as different regions of space-time undergo inflation and form separate bubble universes, there's a chance that some of these bubbles might collide. If such a collision occurred close to our observable universe, it could, in theory, leave a discernible imprint on the cosmic microwave background, CMB, the afterglow of the Big Bang. These imprints might appear as circular anomalies or temperature irregularities in the CMB data. Scientists have actively searched for such signatures using data from missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite. Although a few anomalies have been noted, none have reached the level of statistical confidence necessary to claim detection of a bubble collision. Nevertheless, the ongoing refinement of observational techniques keeps this possibility alive. Another indirect approach involves examining the distribution of physical constants across what would be an ensemble of universes. In many multiverse models, especially those derived from the string theory landscape, each universe in the multiverse may have different values for physical constants such as the strength of gravity, the cosmological constant, or the masses of elementary particles. If the multiverse is real, and if we inhabit a typical universe that permits observers like us, then we might expect to find ourselves living in a universe where the constants are near the edge of the range that allows life to exist. This idea is sometimes explored using Bayesian probability and the anthropic principle, a method known as anthropic reasoning. This type of reasoning, however, is controversial. It requires assumptions about what makes a universe habitable and about what counts as a typical observer. Some scientists argue that anthropic explanations are not really explanations at all. They merely shift the problem rather than solving it. Still, if future cosmological data were to show that the constants in our universe lie in a statistically improbable configuration without anthropic justification, that could weaken the multiverse hypothesis. Conversely, if the constants are found to fall precisely where the anthropic principle predicts they should, that would lend indirect support to the idea. Efforts have also been made to explore how quantum mechanics, particularly the many-worlds interpretation, MWI, might leave some observable traces. One speculative idea is that certain quantum computing applications could be interpreted as leveraging parallel branches of the universe, particularly in the execution of massively parallel computations. Proponents of this view argue that the success of quantum algorithms, such as Shor's algorithm for factoring large numbers, might be seen as indirect evidence for the existence of other worlds. However, this line of reasoning remains speculative and is hotly debated, since alternative interpretations of quantum mechanics can account for the same phenomena without invoking a multiverse. Some researchers are looking for multiverse signals in gravitational waves. In theory, if our universe were to collide with another bubble universe, the resulting disturbance could generate a gravitational wave signature. Gravitational wave astronomy is a relatively new field, and the sensitivity of current detectors like LIGO and Virgo is still too low to detect such exotic events. However, next-generation detectors such as LISA, Laser Interferometer Space Antenna, scheduled for launch in the 2030s, may be able to probe these kinds of signals more effectively. Additionally, certain speculative models suggest that black holes might serve as gateways or even birthplaces for new universes. The idea here is that the singularity inside a black hole might be connected, via a wormhole-like structure, to a newly inflating universe on the other side. This concept, while not confirmed by any empirical evidence, is rooted in attempts to reconcile general relativity and quantum mechanics. If these ideas ever gain more theoretical support or are connected to observable phenomena, such as specific signatures in Hawking radiation, they could potentially offer another way to approach the multiverse question. There's also an emerging area of interest involving simulated universes. While not a multiverse in the traditional cosmological sense, some thinkers propose that if it's possible for advanced civilizations to simulate conscious beings, and if simulations are easier to create than real universes, then statistically we might be living in a simulated world. This simulation argument suggests a kind of multiverse filled with computational universes. Testing this hypothesis is extremely difficult, but some have suggested looking for anomalies in the laws of physics or limitations in computational precision that might hint at an underlying digital structure. Despite the ingenuity of these various approaches, none have yet provided conclusive evidence for the existence of a multiverse. This has led to a re-examination of what it means to test a theory, especially in contexts where direct evidence may be permanently out of reach. Some philosophers of science argue that a theory can still be scientifically valid if it is the best explanation of known facts, even if it is not directly testable. Others worry that this opens the door to unbounded speculation and undermines the empirical foundation of science. Another possible route for confirmation lies not in direct observation of other universes, but in the mathematical coherence and predictive power of the broader theories that imply them. If, for example, string theory or a particular model of quantum gravity is confirmed through other means, and if that theory robustly predicts a multiverse, then the existence of the multiverse may become a scientifically accepted consequence, much like how the existence of black holes was once inferred long before they were observed directly. In summary, while the direct detection of other universes may forever remain beyond our reach, the search for confirmatory evidence continues in several directions. From subtle anomalies in cosmic background radiation to statistical arguments about the values of fundamental constants, to emerging technologies in quantum and gravitational research, scientists are pursuing every available avenue. The road to evidence may be long and uncertain, but the stakes are high. Confirming the multiverse would represent one of the most profound shifts in our understanding of reality since the dawn of modern science. Whether we succeed in finding such evidence or not, the pursuit itself is pushing the boundaries of both physics and philosophy, expanding not only what we know, but how we know it. The potential existence of a multiverse is not only a topic of scientific inquiry, but also one that touches deeply on philosophical and ethical considerations. If our universe is just one among potentially infinite others, each with different physical laws, histories, and perhaps versions of ourselves, the implications for how we understand meaning, identity, morality, and purpose are profound. Philosophical reflection on the multiverse idea stretches the boundaries of metaphysics, epistemology, and ethics, challenging many long-standing assumptions about reality. One of the most immediate philosophical challenges posed by the multiverse hypothesis is the question of identity and individuality. In a multiverse where every possible version of events plays out, there could be countless copies of you, some leading similar lives, others drastically different. What does it mean to be you in such a scenario? Are these other versions truly you? Or are they different people who merely share your memories, biology, or decision histories? Philosophers have long debated the nature of personal identity, whether it is grounded in continuity of consciousness, memory, physical substance, or something else, but the multiverse forces a new lens on the issue. If exact or near-exact versions of ourselves exist elsewhere, what distinguishes them from us, morally or ontologically? This issue leads directly into questions of free will and determinism. In a deterministic universe, Every event is the inevitable result of prior conditions. But in a multiverse, especially in models like the many-worlds interpretation of quantum mechanics, every possible outcome of every decision you make actually occurs, just in a different branch of the multiverse. This gives rise to a peculiar kind of fatalism. Every choice is made, and every consequence unfolds. While this might suggest that choice is an illusion, some philosophers argue the opposite, that free will is preserved across the branches, with each version of you genuinely making their own decisions in their own context. Still, this raises ethical questions. If you also chose differently elsewhere, are you responsible only for the choices in this branch? What does moral accountability mean in a multiverse? Another philosophical domain impacted by the multiverse is ethics and value theory. If there are infinite versions of reality, each containing variations of moral and immoral acts, what does it mean to live a good life? Can actions be judged in a multiverse where for every heroic deed there exists a version where the opposite occurred? Some argue that morality becomes relative in this context, or that it loses meaning entirely. However, others maintain that ethical action still matters immensely within each individual universe. We still live, suffer, and make choices in our local reality. The existence of alternatives doesn't diminish the ethical weight of our experiences. It merely highlights the fragility and uniqueness of our moral context. The multiverse also introduces complex questions in metaphysics, the branch of philosophy concerned with the fundamental nature of being and reality. One major question is whether all universes in a multiverse are equally real. In some models, the other universes are as physically real as ours. In others, they may be potentialities or mathematical constructs. If they are equally real, then the multiverse challenges the idea of a privileged actual reality. This would align with modal realism, a philosophical position that holds that all possible worlds are just as real as the actual world. Philosopher David Lewis famously defended this view, suggesting that possible worlds are not just hypothetical tools for thought, but real, existing entities. For many, this conclusion is too radical, while others embrace it as a necessary implication of serious multiverse thinking. The question of meaning and purpose in a multiverse is also significant. Traditionally, people have found meaning in the idea that life is rare, precious, and perhaps divinely guided. If life is instead just one of infinite possibilities playing out randomly, some worry that this perspective could lead to existential nihilism, the belief that life has no inherent meaning. However, others argue the opposite, that the multiverse makes life even more wondrous. In a reality where everything conceivable happens somewhere, our own experiences, thoughts, and actions take on new layers of significance. We are not insignificant. We are participants in a vast and dynamic cosmic drama. Religious and spiritual beliefs are similarly challenged by the multiverse. Many religions center on the uniqueness of human beings, the singularity of creation, and the presence of a divine plan. If multiple universes exist, each with different histories and perhaps different moral frameworks, then questions arise. Is God present in all universes? Are there universes without divine influence? Do souls traverse universes? These are speculative questions, but they show how the multiverse hypothesis collides with, and potentially reshapes, traditional theological concepts. Some religious thinkers have embraced the idea, seeing it as compatible with a divine being who creates through diversity. Others reject it as incompatible with core doctrines. There's also the epistemological question of how we can know anything in a multiverse. If we are just one instance among infinite alternatives, then our observations and reasoning might be unrepresentative of the larger reality. This could lead to a kind of epistemic skepticism, a doubt about whether our beliefs are justified or whether they merely reflect a peculiar location in the multiverse. Some philosophers have attempted to use probability theory and Bayesian reasoning to overcome this concern, arguing that we should reason based on typicality assumptions, that we are likely to find ourselves in a typical universe. But defining typical in an infinite ensemble is notoriously difficult and potentially circular. Another ethical concern is the risk of scientific irresponsibility if multiverse thinking is misapplied. Critics argue that invoking the multiverse to explain fine-tuning or other phenomena may prematurely end deeper investigation, substituting speculation for rigor. If every outcome occurs somewhere, then virtually anything can be explained post hoc. This risks eroding the standards of scientific proof and could be used to justify weak or unfalsifiable theories. Philosophically, this blurs the line between science and metaphysics and challenges the demarcation problem, how we distinguish science from non-science. Yet despite all these challenges, the multiverse also opens philosophical doors. It encourages pluralism, the idea that reality is richer and more varied than we can imagine. It suggests that we may be part of something far larger and more intricate than previously conceived, and that our concepts of existence, morality, and knowledge may need to evolve accordingly. The multiverse invites us to think beyond traditional boundaries, to entertain new possibilities, and to develop more flexible, expansive frameworks for understanding our place in the cosmos. In conclusion, the philosophical and ethical implications of the multiverse are as vast and varied as the multiverse itself. They force us to confront our assumptions about identity, morality, knowledge, and meaning. They challenge traditional boundaries between science and metaphysics, between what is observable and what is conceivable. Whether or not the multiverse turns out to be physically real, the act of engaging with it philosophically is already reshaping how we think about existence itself. The multiverse is not just a scientific hypothesis. It is a profound philosophical provocation, asking us to reconsider what it means to be, to know, and to matter in a reality that might be far more complex than we ever imagined. The conclusion of any scientific exploration, especially one as vast and speculative as the multiverse hypothesis, serves as both a summation of insights gained and a reflection on the journey itself. After traversing the theoretical, observational, philosophical, and ethical terrains related to the multiverse, we find ourselves not at a firm destination, but rather at a dynamic threshold, one that challenges the very nature of what it means to conclude in the context of such an open-ended question. While we may not yet possess empirical certainty regarding the existence of a multiverse, the inquiry itself has reshaped our scientific boundaries, expanded our philosophical frameworks, and deepened our understanding of the universe we inhabit. First and foremost, we must acknowledge that the multiverse is not a singular idea, but a collection of concepts arising from diverse fields such as quantum mechanics, cosmology, string theory, and mathematics. Each version, the inflationary multiverse, the quantum many-worlds interpretation, the string theory landscape, and even the mathematical universe hypothesis, presents its own structure, implications, and challenges. The fact that so many robust theories independently lead to multiverse-like conclusions suggests that the idea is more than mere speculation. It appears, in fact, to be a natural extrapolation of current theoretical understanding. While that doesn't make it true, it makes it a serious scientific proposal worthy of rigorous consideration. Through this exploration, we've seen that the multiverse may provide answers to some of the most pressing questions in physics and cosmology. Why does our universe have the physical constants it does? Why is it so well suited for life? Why do quantum phenomena behave probabilistically? In some interpretations, the multiverse offers compelling, if controversial, answers. It could explain the fine-tuning of constants via the anthropic principle. It could resolve the apparent randomness of quantum measurements by asserting that all possible outcomes occur, and it might even provide a broader framework in which to understand the origins of space and time themselves. Yet these theoretical promises come with methodological and epistemological challenges. Most notably, the difficulty of empirical verification looms large. If other universes are causally disconnected from ours, how can their existence be tested? The multiverse stretches our conventional scientific methods to their limits, and perhaps beyond them. This has sparked intense debates within the scientific community about the nature of science itself, what counts as a theory, what makes something falsifiable, and whether elegance or explanatory power can ever compensate for a lack of direct observability. The multiverse has become a case study in the evolving philosophy of science, revealing both the strengths and the tensions within our epistemic frameworks. Philosophically, the multiverse reframes human identity and existence. It compels us to ask whether we are unique or one of many iterations, whether choice and morality retain their meaning across infinite realities, and how we define truth in a cosmos that may contain every version of every narrative. For some, the multiverse is existentially unsettling. For others, it is liberating. It allows for the coexistence of freedom and determinism, chaos and order, randomness and necessity. It destabilizes anthropocentric thinking and invites humility in the face of the cosmic unknown. Despite the speculative nature of many multiverse theories, there are concrete research programs actively seeking evidence, or at least indirect support. Scientists continue to analyze the cosmic microwave background for signs of bubble collisions, explore the implications of quantum computing for the many-worlds interpretation, and investigate how black holes, gravitational waves, or high-energy particle collisions might provide clues about higher-dimensional spaces. The scientific enterprise has not given up on testing the untestable. It has simply become more creative, interdisciplinary, and probabilistic in its approaches. Looking ahead, the future of multiverse research will likely depend on advances in both technology and theory. New generations of telescopes, particle accelerators, and gravitational wave detectors could refine our observational capacity, while deeper mathematical and conceptual developments may clarify whether the multiverse is a necessary consequence of fundamental physics or merely one possible interpretation among many. Importantly, the outcome will not hinge on a single yes or no answer. It will emerge from the accumulation of evidence, the evolution of frameworks, and the continuous interplay between imagination and rigor. In the broader cultural and intellectual context, the multiverse reflects a trend in modern science toward greater complexity and pluralism. Just as the Copernican revolution displaced Earth from the center of the universe, and the Darwinian revolution redefined our place in the natural world, the multiverse continues this tradition by suggesting that our entire universe may not be central or unique. Whether this idea proves empirically true or not, it has already enriched our conceptual landscape. It has inspired fiction, fueled philosophical discourse, and challenged dogmas across disciplines. And perhaps that is the most important takeaway. The question, does the multiverse exist, may not yet have a definitive answer, but the pursuit of that answer has value in itself. It pushes science to be bolder, to confront the limits of knowledge, and to explore hypotheses that challenge our deepest intuitions. It reminds us that science is not just a body of facts, but a process, a dialogue between what we know, what we can observe, and what we are willing to imagine. In closing, the multiverse is both a scientific hypothesis and a philosophical mirror. It reflects our curiosity, our desire to understand everything, and our acceptance that the universe may be stranger, larger, and more diverse than we ever expected. Whether or not it is real, the multiverse has already expanded the universe of human thought, and that, in itself, is a kind of reality worth acknowledging. Good night.